4 video segments that I'm going to make on some intricate issues in beam modeling in Catia. Now, the content of this first video is in line with this article that we, expository article that we wrote about maybe 10, 12 years ago, 10 years ago, and it's intended for undergraduate students who want to use Catia. It's the first article that you see here, and let me explain to you what the idea is. Okay, so when it comes to modeling beams, which are interacting with either some other beams or perhaps a solid or a shell, if the beam is not properly offset, then you might think that you're actually modeling it correctly, but in fact it is, although it may run and gives you nice color and numbers, but it may be completely erroneous. For example, if you look at the right-hand side, the top right-hand side, there is a shell or a plate, and this is supported by some I-beams underneath it. If you don't pay attention to the offset of the beam when it comes to modeling it, you may be modeling what you see at the bottom right corner, as opposed to what is supposed to, which is the top right corner. And this has to do with let me see. This has to do with where is the dialog box here? Let me see for a second. Right, the beam dialog box, 1D property dialog box. It has an offset selection here, and if you say it's none, then it may not be doing what you're expecting to do. Okay, so in the case of that particular shell and beam, you create the shell by creating a surface and then meshing the shell element, and then on that plate, on that surface, you draw these lines, and you model these lines with beam elements. However, if you don't specify the offset, the beam is going to be merged, or it's going to not be merged, but it's going to be swamped by the shell elements. Okay, so for the purpose of the present video, I'm going to do a slightly simpler version of this problem. So suppose you have a composite beam, as you see up there, aluminum on top of the steel, and these are, say, let's say, fully bonded together, something like a bimetallic strip, and the dimensions are given on the right-hand side. This particular problem is usually done, this type of problem are usually done in your second year mechanics of material course called area transformation method. And actually, without finite element, you can approximate the stress distribution for a problem like that with area transformation method. And the plot that you see at the bottom left corner is, in fact, the information extracted from that calculation. The left side of this is clamped and the right side is subjected to a moment. Now, let me see for a second. So we're going to do that problem. I got your dimension. So we're going to solve this thing as an assembly problem. Insert a new part, and I'm going to call this thing the top one, which is aluminum. Okay. So right-click properties. Sorry, I'm going to do the first one. I'm going to make it steel, the bottom piece. Steel and steel. Okay, let's call it steel beam. And steel beam. All right, let's go make it. So we go to part design. On a convenient plane, on that vertical plane, I will sketch the cross section of that steel beam, which is a rectangle, something like that. I'm going to dimension it in a minute. First of all, I want this to be sitting on the that axis. So we're going to make this thing coincident. And then we're going to put some dimensions here. So this is going to be 2 inches. And this one is going to be 1 inch. Like this. And we're going to pad it by 10 inches. So we go to part design. And we're going to pad this thing by 10 inches. You can see now. Pad 10 inches. All right. And let's apply material properties on it. Steel, metal, steel on that part, and we close. And mind you, I'm not doing exactly the same properties, Young's modulus here, but I'm going to use the default properties of steel in Catia. Okay, now we're going to go insert our second part, insert a new part, and I'm going to call it aluminum beam. Properties, aluminium beam. Okay, aluminium beam. English pronunciation or spelling, actually, yeah, spelling. So aluminium beam. Okay, and all it is a line. For beam elements, we just define a line and then mesh it with beam elements. So I'm going to draw that line here on the top face of this aluminum of this steel part. Okay, so let's get into it. Let's go make this. On that plane, I will sketch a line that is 10 inches long, exactly in the middle, 10 inches long. Let's make it 10. Where is that? And we say OK, and exit. All right. Now, because I did this thing in a sketch, in order to mesh it with beam elements later on, I have to join it, and the process of joining is done in either wireframe and surface design or generative shape design. So where is that? So we join that line. If you drew this thing as a wireframe, a line going from this point to that point, not as a sketch, then this is redundant. This step is redundant. Now we're going to apply properties of aluminum to this. Aluminum on this part. Yes. And OK. All right. We're done here. So let's go and save this thing. File, save management, save as, desktop. Okay, desktop, new folder. So I'll call it the composite or compound beam. How about that? Compound beam. Although sometimes they refer to it as composite, but really that's not what it is. Compound beam. Okay. Now we're going to go to generative structure analysis. Catia immediately meshes this. Meshes the solid, and we're going to do static analysis. Obviously, I'm going to choose the size of this thing to be 0.2 because I want to be close to the numbers that we use in that paper. Linear element, you can see that's very small. That's good. And all right, now let's mesh the beam, the line. Okay, so where is this beam elements? Right there. See that? Solid shell beam mesh. We select it because we joined it. Actually, it picks it, and this makes it 1 inch long element size. Actually, so let's make it in line, consistent with the mesh on the solid. So I'll make it also 0.2. It doesn't have to be. It's just that if you make it too big, you might have some problems later on with joining the two. Joining meaning creating connections between the two. Okay, the next thing we need to do is to define the cross section of this beam, and this is where the fun begins for this problem. So here's the 1D property. You can see that right there, 1D property. You click on it. First of all, you select the support. Notice that aluminum is picked up. The cross section is rectangular, and this is where you specify the size of the rectangle. So let's make it 2 and 1 and say OK. There's a rectangle, but it's a tilted orientation, so arbitrary orientation, and you have to pick the. You cannot notice that you cannot close this. You cannot close this window. If this was either a tubular or cylindrical beam shaft, basically, so the circular shaft, then you can close it without creating any orientation port. But orientation geometry, you can select this. See that this edge, a vertical edge or horizontal edge or a point, and eventually you can orient it properly. So let me show you what happens if I select this edge, for example, this edge. Watch this red cross section. It's going to tilt. It's going to line it up exactly the way I want it to be. Now, the only problem is that I can, if I run a problem like that after I created my connection and everything, basically the two pieces are merged together, and of course you're going to get numbers, you're going to get color, but it's all nonsense. So what we want to do is we want to create an offset. See that? It says done. So we want to say customize offset. So the amount of offset is specified by this little wrench here. Okay, now you got to look at what you have. First of all, you're using a local coordinate system. If you want non-local, then you check this and you follow the instruction. But you're going local. Local is what you see here, X, Y, Z. Notice that the local coordinate system is not the same as the global coordinate system here. And if you notice that the line must be shifted up by 1 inch, because if you look at the PowerPoint right there, the slide, right now the line is sitting here. You want to shift it up, or to give it an offset. We're not going to shift it up, but we're going to give it an offset in the program. So that is going to be, see, the top 3 numbers. This is start. This means start of the line. The start of the line is, for example, on this side. The end of the line on the other side. You can offset them by different amount, but in this case, I want to move the whole thing up by 1 unit. And 1. So the left side of the beam internally is assumed to be 1 inch above it, above where location it is now, and the right side of the beam is also 1 inch above them. You will not be able to see that on the screen, but internally it's going to be taken into account. All right, and that's it. Okay, now if I run the problem now, well, first of all, let's apply the restraints and the loads here. So this left face of the block is clamped, and the top end, or this end of the line, is also clamped because as beam elements right there. You can see that. Now, when it comes to applying moment, well, I have a choice of applying 10,000 on this, or 10,000 on the beam, or 5,000 on 5,000, because eventually I'm going to tie these two together. So let's do 5,000 on 5,000. So here is a moment on that face, 5,000. Now my units are all screwed up here. It's a Newton meter, so I'm going to type, this is about the x-axis. I'm going to type 5,000 inch by, or pound, pound force per inch. 5,000. LBF by inch. Now, it's going to get converted to a Newton meter because my units are set at with Newton meter units for moment. Of course, you can go to tools option and change it, but that's okay. And you're going to get, I think, half of that. Let's double check this. Yeah. In fact, if you want to see, let's go check it. Tools, options. Okay, I'm going to change my units to pound by inch. So this is parameters and measure, units, and make this thing alphabetically ordered. So click on the magnitude. It's going to sort it for you. So where's the moment? Let's see now. Moment. Instead of Newton meter, I'm going to make it pound force by inch. And now if I check my load that we applied here, it should say 5,000. Right there. Okay, good. And we also apply 5,000 to the end of the beam there. So look, I'm picking these numbers because I want them to be consistent with the stuff in that paper in case you want to go and look at the paper more carefully. Now, if I run it, it will work, but it's all going to be nonsense because the beam will not see the solid. Okay, so we have to create I said these are fully bonded, so we have to create a connection between them. The first component is this line. For the second component is that face. So we created the connection here, right there. Okay, right there. And the type of connection, you can try different things. Some of them will simply not work. Some of them will give you the wrong answer. The one that we want is this fastened one. Okay, you may want to play with these, all of these. When I say all of these, slider will not work, contact will not work because that capability is not available between a line and a surface. Is not available in Catia. Fastened will work. Okay. If you do these, the rigid is going to give you garbage. It will run, but it's going to give you garbage, and same thing with the smooth connection. If you want to know what these things are, you really have to go to documentation, which unfortunately is not very helpful, of Catia, or some references that you can find explaining these things. But fasten is going to work, and which if yeah, there's a connection here. There's a connection. Let's put a fastener here. It has nothing to do with nuts and bolts and these like that. This means they're fully bonded, or well, think about it as welded together, moved together. Now, okay, so let me save my analysis before I run it, which is a good practice. Here's the analysis. Save as in that same folder, compound beam. This is in case you have to kill Catia because or the computer crashes, Catia crashes, then at least you have saved it and then you can access it later. Let's run it. Now let's look at the deflection or displacement right there. Let me look at the deflection first. You can see that. Let's look at the front view. Okay, and let me just look at the beam instead of both of them. So here's mesh 1D. You can see that there is the beam right there. Okay, and if you want to see the solid, where is that? Solid is right here, and of course because they're fastened together, you can't see the difference. They're sitting on top of each other. If you want to look at the deflection, the beam is going to look like this. My graphics card may not give you the right color. This does not look right. These colors, my beam elements, some of the contours are not plotted correctly in my current computer. But if you do the vector plot, vector is a symbol. It does look correct. Now, I strongly suggest you compare these things with the stuff, those numbers in the paper, and you can confirm that they are reasonable. Let me see now. I don't have the table from that paper, but you can go and check it out. If you want to see the beam, so you say, show me both. Where's the beam? right there. And I think I can change this thing to average ISO. Yeah, this one will work correct, but the beam, there's a problem with my beam elements. You can see that for displaying purposes, but this is correct. You can check it with the stuff in that paper, and you see that they will match. Here is the von Mises stress. Now, von Mises stress, of course, can only be plotted for, in Catia, can only be plotted for solid elements and shells, not for beams. Okay. And don't let this thing bother you because you're applying concentrated node, and of course you have to stay away from this end. Okay, and your deflection is right there. You already saw that. Okay. Okay, average ISO. There we are. Now, I showed you the process. You may want to go to that paper and compare the calculations in finite element calculation in more detail with the area transformation method. And in that paper, we are also comparing it with the fully three-dimensional model. In other words, the top is modeled with solid element, aluminum is modeled with solid, and the seal is modeled with solid. And then you can see how different they are. As I said, it's very easy to create good-looking garbage in any software, but you have to know these intricacies because otherwise you may be running, but instead of solving a problem, for example, as I showed you, instead of solving this problem on the left, you're solving the problem below it on the left, or the one on the right, you're solving the problem on the right side below.